Okay, let me share screen now. And then, okay, welcome back to the class. So in the very beginning of the class, one thing to remind again, that I was told that currently not too many students took part in the survey that the USA, I mean University of South Alabama sent you, and I just want to remind you that it may take just 5 minutes. I don't know how long because I cannot see the survey. It may take you just several minutes. If possible, please do them a favor. Just just to check. Oh, sorry. Just to check the survey. So we can later improve the course. Thank you very much. And then what is that? Then let's go back to what to the PCA thing. And, oh, sorry. Before to one more thing to mention, which is the final exam. So today is the last class. First of all, don't forget that the homework due is tomorrow, I believe. And the second thing is tomorrow, I will release the final exam. You will see a folder here called final exam, so it will be released. I really believe it will take you. I mean, if you really follow the class, each class, and code it by yourself, I believe it will take you at the most 1 hour. I mean, because many things. I mean, you will see it's a pretty simple. If you follow the class. But I would still like to set up the due date to be the end of Monday, just in case, in case you have something to do for the weekend or something. However, I would still highly recommend you to start earlier. Don't just because I say it will take you 1 hour, so you work at the night of Monday. What if something you don't understand or something difficult? What if so? Okay, so let's start the class. I want to first solve this issue. Give me 1 second here. So I actually have updated. Let me download them. Have updated the codes, and then remember. Let me just download the code first, and then let me go to 11, and then downloads is here. This is 11. Replace. If you have already downloaded the slides of lectures 11 and 12, please re-download the newest version. Sorry about it because I made some very simple changes. So first of all, remember this one. Let me open the code here. Where's my sorry, Anaconda is here. Let me open my code here. Okay. So remember in the last class, there's an issue that we cannot run this example, right? And after a class, I checked it. Okay, it's right here. So where let me see. No, this is something for me to just tune the code here. And you may not believe that actually this code, there's nothing wrong. I mean, simply because because when I write the code, I was using another computer, which, is way faster. This computer, this computer, it is not that fast. So that might, so sorry about it. So that might be the reason for it to be slow. However, here I actually have modified the code here. Let me make it bigger. Because using this way, I realize it will be way easier. I believe inside there must be some code optimization instead of like me brutally for I in row, for in J in column, something like that. We can check it here. Let me just, this one covers me. Okay, so what I can do here is that here, everything's still here, nothing changed. Image arrays here. So in the K list, what I'm gonna do is here, give me 1 second. So remember, this is my k-means clustering, the training set here, centrals here, and from here, I actually don't need those things. I can actually use a pretty simple structure to make it. So I can directly get image clustered equals to this. So remember, we've already got the centroids, which is this model.cluster centroids. So this is centroids. However, since our image, is I believe which image I use for training. I believe MR scan, right? The tumor. I mean the brain scan here is a tumor. Okay, so now what I want to do is I'm gonna directly use clusters this, but here what I'm gonna have is gonna have the labels. So labels means for each pixel, what is the central label? The label of the centroid. So it will be, let's say, centroid 1, centroid 2, centroid 3, and then cluster centers, it saves actually what? The labels. So sorry, it saves the centroids. So for example, let me see if I give me 1 second. Let me just make one example here. Here to make my life easier, let's suppose, I just why don't I do it like this one? 1 second. Since here is what? Since here's a notebook, so I can simply do this. I don't need to have, let's just use another cell to, oh wait, I need to have all these things. Okay. Okay, so now let me open the line numbers again. Okay, so now I have let me see, I indent. I have all these. In the beginning, it is nothing. It's just these things. Okay, so now I don't need a K list or whatever. I just do one thing, which is, let's say, make a fixed K. Let's say K equal to 2. Okay, so now let's say K equal to 2, and then here model clusters, and I even don't plot anything. Because I just want to show you the things. So image cluster equal to actually I even don't need this one. I'm gonna directly say model.cluster. So I'm gonna directly print it. Oh, sorry. I'm gonna directly print it. And you will see how it looks like. Okay, wait. Oh, no. L can simply be equal to K list. Can equal to 2. Okay. 1 second. Image read, image path. So the path is right here. Okay, so this is our original image, and I'll keep the axis here on purpose, just to show you the size. And here, this is a centroid. You can see that this is nothing because here my K means clusters, my K equal to 2. So it's gonna be 2D. If my K equal to 10, then it's gonna be 10D. Yeah, I mean, when I give me 1 second, 1 second. When I say 10D, that when I say 10D, that means how many clusters. So this just shows you the cluster. But what if I print this? I print a label. Wait, let me see. Model dot label underscore should be label. Yes. If I print it this way, so here I even don't to print anything, just to make my life very simple. Let me see here. Let's say I don't need any of these things. Print image dot shape. Okay, so let's say I don't need any of this. Okay, and you can see labels like this way. And then if we can definitely print the shape of the labels, and you can see it's this. In other words, what I mean, that means for each pixel, remember last time we calculated the pixel of this, I can also, let's say, print x dot shape. Okay, so x not defined. Oh, because I haven't wrote this one. Image, not x, image dot shape. Okay, so remember last time we did it, this number times this number equal to this number. In other words, label simply means for each pixel, which centroid you belong to. Okay, now we can go back to this part. So in this part, where is, let me see. Okay, here we go. So the clusters is what? I can directly put a model dot labels here. So what that means? This means, hey, I for each pixel, I have a label, right? I have so many labels, and then put the labels to the clusters. So in other words, this will give me what? This will give me the shape of, let me see, the shape of 51255. And then each row represents an RGB bit, right? And however, this image clustered is something that I'm gonna plot. So to this end, I have to reshape it so that I will make the reshape of the image dot shape, so that after this, I can directly, I'm gonna add a subplot and then I can directly plot it. Well, however, be careful of one interesting thing, that if we are writing this way, remember before we have centroid dot as type int to make centroid as int. If you're writing this way, the plot here, image show, may fail. Why? Because there's no guarantee that the centroids are are like integers. So to this end, you can use two methods. You can either so for example, let me just run it. You will see this one. Let me see whether everything's correct. Yeah, you will probably see this one gonna fail. It was showing an error because of whoa, sorry. I don't have to, because last time I was testing here, I don't have to print the K anymore. And then let me see what kind of things did I print here. Image the shape. I don't need to print the shape here as well. And then define here path to, let's run it. Okay. So you see here, these things. Let me take the things out, the plots out. Plot PT. So, but you can see these are empty. Why? Because for image show, this method, it can have two mode. Mode number one is that in this, the matrix or tensor input, it must be a float between 0 and 1. Or another mode is it takes RGB as integers. So we can either do it as this number divided by 255. This will, force the number, every number in the matrix to be between 0 and 1, or you can make it to be as type integer, the same thing. Let me run this one. And indeed, you see the speed improvement. The same computer. I'm not cheating like use another computer or something. It is the same computer. And you can see a big improvement in the speed. Now it's so fast. And then you can use this method, or let's say you are gonna say, no, I'm gonna use mode number 2, which is just RGB, but I'm gonna make push everything to integers. Oh, figure 2. Here we go. So both ways are the same. So this solved the issue in the K-means clustering. That made me pretty upset last time actually. And after the class, I wrote something there to just tune the code, and I realized that I just waited for about 10 minutes something. It finally came, but the speed was too slow, and this method is actually way faster. Okay, so this is the issue we showed. Let me save it. We showed in the K-means clustering. So now we can go to the PCA. I will create a new notebook, PCA. Lecture 12, PCA. Okay, but before here's another story. Still, let's go to PCA. Please download the newest version of PCA as well, in which I add 2 more slides, which is to show a detailed decomposition of the code of the image. Okay, let's first give a very fast review of the PCA. So we use the 2 examples in the very beginning. Example number 1 is Steve Jobs, and we want to show so first of all, sorry about this. First of all, the idea of this is to do the data dimension reduction. The data dimension for pictures means pixels actually. So suppose this pixel, for example, it's 750 times 1296. So we totally have almost 972,000 pixels. And then technically each pixel can represent a number, can represent an RGB color technically. So technically, I will have so many dimensions, but I don't want it. I want to capture the important information in this pixel, in this image, and then I just want to recompose these things. So the idea is that I want to reduce the dimension from, for example, 972,000 to a much smaller number. And meanwhile, I want to keep the most important information. Then immediately the question is, how do you define the most important information? Like Steve Jobs, not Steve Jobs, for everybody, the most important information is the face. For Steve Jobs specifically, Apple is another very important information. So that's the thing. And the second example is some data like this way. So our original coordinate is the X and the Y coordinate. You can see here, original feature 1, original feature 2. But the truth is this group of data, it's so flat, right? So immediately I may consider, hey, why don't I just, create the coordinate like this way, V1 to V2. And since V2 compared with V1 is so small, it's likely that I only need a 1D, which is a V1 to describe this data set. I can ignore V2 so that I will have one-dimensional data instead of two-dimensional data. Okay, so these are the ideas of the SVM. Not SVM, PCA. And here we have something, this is some very simple things, which is a projection, which is in order, suppose I have the current coordinate is I1, I2. I want to, express the same data X in the V1, V2 coordinate. What are the coordinate? Nothing but inner product. But don't forget one thing here that I use the same origin. And that's the reason why later you will see I will move the X bar, which is the mean of all the features, so that I will always guarantee that they have the same origin, and hence it's going to be just a rotation. Otherwise, it's going to be a chaos. So now we only have the rotation after the shift to the mean. Okay, this is something similar in 3D. And then let's have a look at some mathematical models. First of all, what does important information mean? So here we want to mention that an important information means towards the direction which data differ the most. This can also similar like this, like different people's picture. If you see this part, they're always the same, similar I would say. But the face, in the direction of the face, people differ the most. And similarly, you can see here for this data set, this V1 direction, in this V1 direction, the data set differs the most. Okay, so we use this one to define the important information. For PCA, I want to find the direction. And then because we say differ the most, so a very intuitive method to measure it is what? The variance of a data set. That shows like how like the data kind of differ from each other, or how it span in the space. And then so that the covariance, be careful here because we have many dimensions. So we are going to use the covariance matrix. So variance means only usually, if we say variance means it's a 1D, but if it's D dimensions, we're going to say covariance. The covariance matrix definition is this one. And then here use some super simple mathematics. You can get the covariance matrix here. To make my life easier, I'll still in the following, I still call it a variance matrix, but technically it should be the covariance matrix. Okay, and then remember we want to shift, like here, we want to shift the origin of the new coordinate to the same thing. So to the same origin here, so that it will have only a rotation. So we will calculate z. Z is to shift the mean to the original data set to 0, and be very careful that this Z matrix is actually sorry, it should not be P, it should be D. Here's a typo, I just realized it. It's D dimensioned. Here ZT becomes D times N. If it's Z, it should be N by Z. Okay, be very careful. And it is the mean in terms of the features. In other words, suppose I have D features, so I have D different numbers. It's not in terms of the data, like N data. So that's the thing. Each feature, so I have one thing. So I have the Z here, and then give me 1 second. By the covariance matrix here, I can write, my final equation like this way. And then here's an example, like how can we do the rotation? And then we first calculate the Z, which is the shift matrix, and then we calculate the V. And then you can see here, I use some simple example to show you this formula is correct because this formula, the result is exactly the same if we calculate directly in the 1D. So this is the same. And then the next thing is that we mentioned that we want to find the most important. In other words, it should be the direction that my data set diverges the most, right? Or let's say differ the most. And by our definition, it should be the biggest the biggest variance here. And hence I can write it in this way. And then here the KKT condition, which is an optimization technique for doing nonlinear for doing nonlinear optimizations. But here a special case is because here ZTZ are constant. I know the constant matrix. Here V is the direction, which is a variable, decision variable, and hence you can see that this is actually what a quadratic formula. It's the same like ax squared. Let's say I want to ask you maximize, let's say 3x squared. Well, what is the same? Something like that. And then of course it won't be 3x squared. It will be something kind of like, and then you are gonna give a constraint. Otherwise, your 3x squared, you don't have the maximum number. So something like this, because of quadratic, so that we can always get what get the global optimal condition directly, because there's going to be only one, the local equal to global. And then I have these 4 conditions. Since here I only have one equality constraint, so I only have the stationarity constraint and the complementary slackness constraint. And then we can explicitly write these two to be this way. And then we see this formula, and then reminding me what eigenvalue and eigenvectors. And then because of this one, I can immediately write this equal to lambda1, where lambda1 is the largest eigenvalue. In other words, we know that the so-called principal components are actually nothing but the eigenvalues as the objective function, and the eigenvectors as my ith PCs of ZTZ, the matrix ZTZ. In other words, lambda1, which is the biggest eigenvalue, its corresponding vector is my PC1, the first principal component. Of course, the first means the most important one. Lambda2, which is which is the second largest eigenvalue, the corresponding eigenvector is my second PC. And until your lambda d. So the d's lambda, which is of course the smallest lambda, and the corresponding eigenvector is the last PC, the least important PC. So that's the thing. And here, if you want to know more mathematics, you can just check here, in which I also mentioned singular value decomposition, SVD, and they have a direct correlation. But here, due to time, I'm not gonna mention it here. And then the score of the JSPC means the Z VJ. That means, let's say my vector that means the JPC and then Z matrix is just the centered matrix. Be careful, okay? Z is x minus x bar, so this is Z. Okay, so where it is? So the score simply means, well, for let's say each data, what is score on the JPC. So that's the thing. It's actually nothing but a projection, just a projection. I mean shifted projection, because you need to shift it to the center. Okay, so now we have what? Let me see. I remember I ended here last time, right? Yes, I ended here. So now I already have calculated the what? The variance, and then also the PCs. And here I can calculate the total variance. The total variance means the total variance. So it is nothing but the summation of all these things. So that means the variance of the data projected onto each VI, where VJ, where VJ is the JPC. It is, as we mentioned here, the variance has nothing, just the lambda J, which means just the eigen value, and hence I just need to sum all of them. Of course, divided by n, you can ignore it, which is just a constant, it doesn't matter. And then this is the total variance, but we will have we'll try to do the data reduction, dimensional deduction. So that clearly I want to use all the dimensions D, because otherwise my original image, let's say it's a 1 million dimensions. What's the point for me to convert it into another space and still keep a 1 million dimension? I mean, I'm just wasting my time. So what I'm gonna do is that instead of take all the D, let's say 1 million total number of PC's principal components, I will only take a K of them. K will be a very small number, for example, K equal to 100. So from 1 million to 100, which is a shrinkage of 10,000 times, right? But the thing is, why 100? Why don't you take 101? Why don't you take 99? So there should be a standard to determine how many PCs are adequate. So how to determine it? We're going to use this one, the ratio of the explained variance. So my total variance is this, the summation of the lambda j. I mean, again, 1 over n you can ignore because, they can cancel each other. So now I'm going to, gradually start, let's say, start from PC1 till, the second PC. I mean, I'm going to sum all of them. Let's say the first one is PC1, the second one is PC1 plus PC2, the third one is PC1 plus PC2 plus PC3, blah, blah, blah. For each K, I'm going to calculate the ratio of the explained variance. That means, so this is the total in the denominator, it's the total variance, and in the numerator, it's the variance that already I'm currently applied, or let's say more formally, it's called explained. The variance that I've already explained use up to the case PC. Then I'm gonna see the ratio, how large it is, and I will have a threshold alpha. If this number is greater than, I should say this, I will gradually increase K from 1 to 2, 3, 4, 5, blah, blah, blah. Once the first number that this ratio is greater than the threshold alpha, I'm going to fix that K. In other words, I'm going to choose the smallest K of the PCs from PC1 to PCK, such that this K satisfies RK greater than or equal to the threshold alpha. Then I'm going to stop. So that's the thing. And here I show the example, which is 1, 2, 3, 4, 5, these 5 data, and then I manually calculate X bar. Again, be careful, X bar is in terms of features, okay, not in terms of axis. You cannot say, oh, X bar, so the summation of 5 data divided by 5. No, it's it's not. It is for each feature. Here I have feature 1, feature 2, feature 3. I have 3 features. So for each feature, I have a bar, which let's say the first one is 10 plus 5 plus 9 plus -9 plus 5 divided by 5. So the first one, the second one, the third one, and then you get X minus X bar, you get a Z, and then you calculate a ZTZ and calculate the eigenvalues and eigenvectors, and then you have these 3 eigenvalues with corresponding to these 3 eigenvectors. So I make the color the same to make it easier to recognize. So you can see this is the biggest eigenvalue, the second biggest eigenvalue, the smallest eigenvalue, so that, according to our previous analysis, what shall we do? This one should be lambda 1, right? And the corresponding, the cyan color of this eigenvector, this should be our first PC. This one should be the second largest eigenvalue, and hence this one is the second PC. The third one and this one the third PC. Here we go. Okay, now suppose excuse me, suppose my threshold alpha is 90%. I'm gonna ask you, hey, when shall we stop? Okay, first of all, I calculate R1. That means I only use the first one PC, which is of course the first PC. The explained variance is 86.6 something, and then the total explained variance is this one. I calculate the ratio, I realize it's only 74.59%. It's smaller than 90%. Okay, continue. I'm going to consider the first 2 PCs, which is PC1, the eigenvalue plus PC2, the eigenvalue, excuse me, divided by the total explained variance. And now I found that the explained ratio, the ratio of the explained variance has been 99.36%, which is already bigger than 90% my threshold. And hence I'm gonna say, okay, in this case, I only need 2 PCs. In other words, I can reduce the dimension from 3D to 2D. So that's the thing. Of course, if alpha equal to 70%, so your first principal component is already enough to explain. So that's the whole thing, okay? So now here, for this specific example, I'm gonna show how can you get a rent here. Lucky thing is that the PCA, I mean scikit-learn decomposition PCA, it already includes everything there. So you don't need to recalculate everything again. let me see. Since this one's pretty simple, I'm even lazy to code it. Let me see here. Yeah, since this one pretty simple, to save our time, let me directly just based on this one. So first of all, you're gonna import MP and also this one, which is a scikit-learn dot decomposition imports PCA. And here I'm gonna put the file data here. And that's the reason why I don't want to code it here, because I always cannot remember the number sign to cheat it. So and then you just write model equal to PCA model.fit x, similar things, and then here we can just get the model components. This components is a 2D vector, which saves the principal components. And then here I can print PCs, which are, so my principal components are give me 1 second. Yeah, my principal components are right here. Here PCs means components here. So I have this one, this one, this one, and then you can compare with our results, and they're the same. Of course, here I show equal to 3, but why it show only 2 digits? Oh, that's interesting. I'm not sure, because technically it should be. Oh, okay. Because this is probably 680. Is it? Yeah, it is. You can see it. It's 680, 0.7, negative 0.7. And also, oh, by the way, so you can see the signs are a bit different. It doesn't matter, because as long as there's a 1, I mean the total number of negative sign multiplication equal to here. So I shall say this way. So it's the same order or even number, because you think about it, here's only 1 negative sign, here's also 1. You can well, here's, let me see, what here's 2 negative sign. Let me think about it. Okay, I know why. So again, this is not a big deal. The reason here is because when we say, let me give you an example you immediately understand. Let's say here. So here I define this one to be V1, this one to be V2, right? But I can do the same thing like here. I can do it. Let me find a blue color. Oh my God, Zillow, give me a blue color. Okay, so I can let me use a yellow color to make it, I can define this one to be V1 as well, isn't it? That's a reason why sometimes the sign is going to be different. Because it's simply just this kind of directions. You can make this one to be V1, this one to be V2, or you can even make it like this way. You say like, okay, I don't like this V2 direction. I use this V2 direction. I mean the same thing. So actually we don't kind of like really take care of the signs. So this is the first PC. The second PC is here. You can see the results. Second PC is here, and the third PC is here. You can see all of them actually are the same. And then we need to check several this kind of outputs. The first thing is explain the variance. So here the explain the variance of each one are 121, this and this. And then we can calculate the explain variance ratio. Sorry, ratio, not ratio, ratio, no n. So the ratio gonna be like this way. So the first PC explained the variance as 74.6%. And you can see 74.6%. The second one, 0.248. So the summation of this one is what? It's 99.4. And you can see 99.36. So that's the thing. In other words, our definition, the explained ratio here, RK, is simply just summation of the first K, components here. In scikit-learn, each the explained variance is towards PC wise. In other words, each PC, what is that? How to calculate it? Super simple. The corresponding lambda divided by only one lambda, let's say lambda j, no sigma, okay? Lambda j divided by the total variance. So that's how scikit-learn calculate it. And then what is that? The data coordinate. So the data coordinate in the PCs, this is the transform. In other words, it is this z. Let me see. It should be the zv. Well, let me see where it is. Let me see. It should be the z V matrix. The V matrix is here. Let me see, where did I? Okay, here we go. The ZV matrix, where the V matrix is just V1, V2, V3 transpose. As a real transpose, Again, it's because Python, that's the Python definition, okay? Python defined everything to be the row vectors instead of column vectors. But in mathematics, usually when we say a vector, we by default we assume it's column vector. So that's the reason why it's in this way. In other words, V1 is this, the second row is going to be V2, the third, I mean, it's exactly here. So this PC is this matrix components, this one model.components, this is the V matrix, and then the Z, here we go. In other words, the projected for this PC's basis is model.transfer. It's nothing but the Z matrix times this one. What's the meaning? Meaning that for each data, what's the projected coordinate? That's after shifting. So for example, my original first data is 10, 11, 10, right? This 10, 11, 10 are the coordinates on my original space. Okay, now in my PC space, after shifting means after moving everything to the center, they're negative 10.8, 7.9, and then negative 0.07. So this is the meaning. Okay, now have a look at the second one. I will code the second one here because here we use the quiver, and I believe I also use the tag. Did I use the text? Quiver is nothing, just put those kind of arrows, and then we can plot actually the what the PCs. Okay, so let me see here. Okay. So we need first of all let me the numbers. I really don't understand why it doesn't show the number by default. So that I will have import numpy XMP, import all those kind of things, matplot. And then I'm to scikit-learn decomposition. Come on. Okay, decomposition, import PCA. And then to make my life easier, I will do this. Okay, so first of all, what I need to do is I need to generate some data. Okay, great, I forgot again. So let me see what are the oh my god. Okay, so I'm gonna have x equal to np.random.multivariate normal. And then 10 for 1681. And then I generate just 3,000 data. Great. Again, be careful. Since here we do not have labels, so I don't need to generate another Y. Remember before we did the Y's here, because here again it's unsupervised cluster, unsupervised learning. Here I need to set up the MP print options. Okay, now I will actually now I don't need it anymore. So after it, I will calculate what? I will calculate the mean. The mean is just the same. Remember in the Z, I will have Z equal to X minus X bar, something like that. Remember it? But the lucky thing is I don't need to, write everything by myself. Python let everything do it for me. So it's gonna be just MP dot mean of your X. But be very careful here again is that Python, the X data here is gonna be what? It's gonna be each row gonna be a data, and hence my mean axis should be 0 because each row has, let's say, D features. Again, our X bar, the mean is in terms of the features. So for example, you can simply just X dot shape, and then you can even print, let's say, okay, and then here you can even print X bar. X bar must be 2D. You see it? So although I have 3,000 data, but I only have 2 features. So the axis is 0. Be careful about this. Okay, now I have generated the data. I need to do what? I need to train the model, right? I'm gonna say train PCA. Okay, so I'm gonna have what? I'm gonna have model equal to PCA. And then model dot fit X. So now I fix it, and then I can print many things. Let me see what I printed here. I believe PCs. I must have model, yeah, printer PCs. Let's say PCs model dot components. Here we go. So I found that the biggest the two important directions are the direction that the data diverse the most is this direction, and this is the second most. So these are the things. So after it, I actually need to plot it. I believe here. I believe here after, let me see, the results are like this way. I plot the four things. So the first thing is the data in the original feature space. I use a quiver to plot the directions, and then let me see, data in the PC basis. Be careful of this. So original feature one, original feature two, first PC, second PC. So here the coordinate has already changed. And then I can project it onto the first PC, looks like this way, project onto the second PC like this way. And anyway, I guess it's better for me directly to write the code instead of just, okay, now let's say plot let's say original data, or the original data in the original let's say feature space. Okay, so first of all, figure HPLT, the figure, and then add a sub here, because we have the what 2x2, 3, 2, 1, so that I can just plot PLT x0, x1, and then let me use R red color, and then label the let's say the original, let's say the observed data, because the reason you will see later why I call it observed data. So here, let me just set let's say original feature one, and also original not set title, set x label, y label, and then set title here. I can have what data in the original feature space. Okay, so here we go. So dot. Because if there's no dot, it will connect different points. Okay, here's the thing. And one more thing, you know what? I need to make the axis equal, because otherwise you can see the scale. The scale is something wrong. You can see here the scales, here's on 16, but here's 40, but the length like this way, so that I will need to, let me see, put a scale here. AX dot axis, let's say equal. Okay, now it should be the correct one. Yeah, this is correct. So I can. So this is the original data. And the thing is, I need to plot the PCs, right? In order to plot the PCs, I need to get to the, let me write it this way. So to express different sections, so that I will need to write the what. I need to use the quiver. Plot the two PCs in the original space, as original feature space. Okay, so now I will use x.quiver. So first of all, you can see the help here. So basically, it will ask you where you would put the start point of the xy of the quiver, the arrow here, and then it will ask you the UVCs are actually to kind of determine the end point of your arrow. So think about it, when you're plotting arrow and arrow here, you're gonna have a start point and then an end point, right? So this will be your start point, this will be your end point, something like that. And then you need to also need to tell, Python how large the arrow itself is, because the whole thing includes the line plus the arrow. So the arrow. So this is the thing. So let me directly make this one. So again, because we will we've already shifted the thing there, which is x bar, which is the mean of the features. So I'll always start from the the middle point, x bar 1. So here I define this one, and then I do define this one. This one is also simple. Why? Because I've already have like model the components. So clearly it's gonna be 0, 0 for the first PC, okay? Model dot components and 0, 1. So that I have this point. Okay, then I will have what? This is something unit equal to xy. This is something unit, sorry, equal to xy. Let me just want to make sure. Yes, units z order. Okay, I will keep z order here. So like here I didn't write z order as well. Let me just temporarily keep it, and then you will see what happens and why do we need a z order. So unit xy, that means it's just the absolute coordinate. Quiver, a matplotlib like Quiver provides you many different reference way, but to save my life, I will use this one because otherwise you will see something very interesting. And that scale equal to what did I say here? 0.05. So regarding the mean of the scale, it's just you tell this one, then corresponding to how large the arrow itself is, it's gonna scale the length of this. So here is actually I tried the different parameters and I tuned here. The reason this one, the smaller this one is, the longer it's gonna be, not the bigger it's gonna be. So that I set up like this way so that I will have the first PC a bit longer and the second PC a bit shorter. So, but anyway, let's temporarily use the parameters here. And then let me see, I have the color equal to let me see, one is green, one is blue probably. Yes, one is green here. And I will have the label equal to let's say first PC. Okay, let me just erase this one so I can copy and paste and I'll plot the second PC. Okay, the second PC is gonna be 1, 0 because I have my second PC here and second PC. This is gonna be blue, as I just mentioned. This is gonna be 0, 1. Okay, so now I should have let me see here. Legend here, and then let me try it. Let's see other. Okay, here we go. Indeed. And you see something is missed. Why just missed? Okay, that's the reason why we need a z order. So z order means how would you plot it? Plot everything. So if I put a z order equal to, let's say 2 here, it doesn't matter, and I need another 2 z orders here. So this tells Python that you're gonna use this order to plot everything. Let's say here I can use, let's say 5, and then I make this z order to be bigger than 5, the order equal to, let's say 6. Let's plot it. Here we go. See it? So the reason before it was covered is because it cannot differentiate connectivity orders here. So now I tell it, hey, plot this one first, then plot this one, then plot this one. So this one will be up of this one. Okay, so now I have the two PCs. Of course, you can use ax.text. Remember what we did in classification to write the things there. I'm just lazy to calculate, the direction, the coordinate something here. So in this way, we have plotted what the first image, which is again the original, the observed data. Wait a minute. What I feel okay? I'd better put it here. Let me see if I put it here. If I put it here. Yeah, here we go. So this is gonna be like more fair. Let me see. Why I still feel, I know why, probably because I use a scale. I use scale here. Looks like makes it looks not that equal. Better than nothing. Okay. So here is the original one. So now I want to plot what? I want to plot the observed data and let's say PC basis. Let's say PC basis. Okay, so first of all, I can create a figure, but actually let me equal to model dot transfer. Transfer X again means what? Means this. ZV, okay, so that I will project all my data into my PC space, and then each row is actually the new the new coordinates of each data. The new basis means the PC basis. Okay, so now I have this one, and now I can add a figure, and then I will do what I have. Will make the plot. Be very careful here. It's going to be the PC, so you can directly use this one. X PC 1. And then I can use, and then label equal to the other variable data again. And then x dot axis equal x dot legend. And one of the most important thing in this specific example is that I need to set an X label and a Y label. Be very careful. This is gonna be first PC. Second PC. Okay, these are things. I can let me see. What did I do here? Set a title. Okay, I can set up a title here. Let's say data in the PC basis. Here we go. Huh? What is wrong? Transfer. Oh my goodness. Let me just first close everything and then do it again. Okay. Transform. Well, how can I write? Transform. Okay, here we go. Still wrong. Equal. Wait. Keyboard. Great. From teaching this class, I learned a lesson that keyboard is extremely important. So, wait. How come it looks like this way? This one's correct. Let me just rerun it again. Okay, here we go. So this is the observed data. You can see that from the first and second PC. And indeed, this one actually it's pretty equal, the axis level. And you can see from this is the first PC in this direction, the variance is this, or we can say the difference is this. But in this second PC direction, it's so small. You see what I mean? And hence we may really consider to make it to be on 1D, which is only on the first PC. So here, let me see. Here, let me continue. I believe I also plotted the other two. Yeah, I plotted data projected onto the first PC and onto the second PC. So you can see the differences here. Let me see. Actually, this is pretty simple. Okay. To save my time, I'm gonna only show you the first two plots because these things are super simple. The trick here, I believe, is that I used give me 1 second. For how did I plot the other two? I use the zeros so that the y-axis here you can see they're all in terms of 0. So that in this plot I just assume all the y-axis are 0. So I only plot the x-axis. Here similar. I lock all the x-axis to be 0, and I only plot the y-axis. So you're gonna see something here. For the code, it's extremely simple. You can just check here. Okay. So the project results are here. So this shows a very basic things how to plot the PCs. And remember, here we mentioned that we don't have to, waste the time to reproject to the full space. A full space means d-dimensional space. We want to do the data dimension reduction, right? Okay, so do data dimension reduction, I will project it on the K. Let's say suppose a D equals 1 million, let's say a picture. So I only want to use 100 feature to show the 1 million. But well, you now already have everything. You have the V1 to V100. You calculate, explain the ratio. You realize that it's greater than your threshold alpha. Everything's good. You have your Z matrix. But let's say an image. How do you recover the data, right? You cannot just tell me, okay, here's a PCA. Here's my PC. So all mathematics done. No, what I need is not like this way. What I need is to reconstruct our data. Specifically, if it's a music, I want you to replay the music. If it's a image, show me the result after your data dimensional reduction. What is a new picture? I want you to reconstruct the data in, based on the original data, based on my case, first K PCs. So that's the thing. How can we reconstruct it? Super simple. So XPC as ZV as we just mentioned here, this one, which you can just use transform, you can make it. And then XPC, be careful, it's N by K. Okay, N means I have total N data, training data or observed data. K means now I only use K dimensional data to recover the D dimensional data. Have a look at here. We want to use the first K PCs to represent the raw data. D is a very big number compared with K. Let's say 1 million versus 100, something like that. So how can I use the K small dimensional data to recover it? Okay, so now we have X reconstructed equal to this. So remember XPC equals to ZV already. So in order to project it to back to the original space, I just need to give a times VT. Why? Because my Z equal to sorry, my XPC equal to ZV. And the V dimensional is Z dimensional is what? Is N by sorry, my Z dimensional space, come on a second, because I always get confused about the T, because in Python everything is the opposite. Okay, so Z is here, and the ZT is N by give me 1 second. ZT is this is D, okay, D by N, and hence Z is N by D here. Okay, Z is N by D. And your V dimensional is what? V dimensional is, let me think about it. It should be D by K, right? And hence I should write here are some dimensional errors. Here technically I should write VT. I should not write V. I should write like the VT here. And hence your XPC is N by give me 1 second. Give me 1 second. Your VT is going to be K by. Okay, sorry about it. Okay, now it's correct. It's correct. So your XPC dimensional is N by K now, and then your V is D by K, and hence VT is K by D, and hence your result going to be what? Your result going to be N by D. So this is the N by D, and then your X bar is still the mean of that. Again, remember X bar is the mean in terms of feature. So our X bar, the dimensional gonna be N by D as well, meaning that I have N data, N observed data, and all of them are the same. You can see here, there's no typo here. Each row are exactly the same, X bar, X bar, X bar. And then how to calculate X bar? It's the mean or in terms of feature. So that's the thing. Okay, so this VTV is called a projection matrix. If you have learned something like advanced topics of linear algebra, this VTV is indeed a projection in terms of different bases of the space. It will take some hours, many minutes to explain. There are a lot of stories about the projection matrix or mathematical things, but anyway, here I would ignore it. I'm not sure what I included in my this part, but if you're interested, you can find some topics here. Okay, then let me see here. Then as a special case, if my K equal to D, and then this projection matrix will be an identity matrix, which means your R in X in reconstruct gonna be exactly the same to be X. Why? Because remember, my what is X minus X bars. Here you plus X bars, so it's minus and plus. They're gonna vanish, so it's gonna be X as well. Of course, in the practical cases, I'm not gonna have K equal to D. I will have K less than or equal to D. And hence this is going to be a dimensional dimensional reduction. And in most cases, it will be a bit different, but you can see the result is still pretty good. Okay, so let me have a look here. So applications of PCA, first of all, if you can make the K to be 2 or 3, so that we can always plot it. And another thing is that so this is the first of all for data visualization. The second thing is for classification or clustering, because I can make it to be, let's say, much smaller
make the K compared with D. So I can use this one to, use the K dimensional space to do based on the new data. Then I will do clustering or classification. This will make our work of clustering or classification much more efficient. Why? Because I have a data dimensional reduction. Think about it. Before to do classification, let's say, and under 1 million dimensional space. Now you only need to do classification in 100 dimensional space. Which one will be faster? So that's the thing. However, be careful that technically the PCA still belongs to unsupervised learning. It's not a supervised learning. The only thing we do here is we just want to take advantage of the new PC basis so that I can make the dimension to be much lower. So based on the lower dimensional space, I do no matter clustering or do classification will be faster. So this is logic. You cannot say because I can do this, so we consider it as like a classification. It's supervised learning. No, it's not. It's still unsupervised learning. Okay, let's see some examples here. So here we have the PCA based for the handwritten digits. Remember this one? We did in which class? I forgot. In SVM, I believe. Yes, SVM. So that we can actually find out the codes there simply because I'm just lazy. I just want to copy and paste. Which one is SVM? Here. Okay. So let's see. Where are my? Is it my last example probably? Let me see here. Yeah, here are my things. Okay, so let me just copy and paste here, but I need to be careful because when I prepare the slides, I remember there's something wrong. First of all, I do need to have things. Let me see MP here. I don't need SVC anymore. Instead, I need to have what? I need to have the PCA things so I can learn decomposition, import PCA. Low digits. And here I don't need this one anymore because I'm not gonna plot it anymore. So that first of all, I'm gonna have the digits here, and then let me see. Sorry about it. Let me have a look. I believe I coded only 0, 1, 2. Yeah, only 0, 1, 2. So here, where is here only load, so I need n class equal to 3. That means for the data, the digits only need to have 0, 1, 2, 3 numbers instead of from 0 to 9. So that I'm gonna have n class equal to 3. And then I load this one. Okay, so then I can have let me give me 1 second. Let me do the step by step. I can actually print it. So, okay, so here you can see, first of all, it's still, the features are still 64. And so in other words, the dimension of the data is 64. But here, instead of like, remember before our training data 17 something, 1,700 something. Here, 1, 2, 3, it includes only 537 samples. So I'm gonna do things, just the samples here. And then let me see, I'm gonna do what? Let me think about it. So I will have all this party image. Okay, so also here there's a change that because give me 1 second, I probably will need to I will need to have this list so that I will have basically because later we will plot it, I need to know the indices for digits 0, digits 1, and the digits 2 so that I will have list 0. These are gonna be index, so I will write the for inside of I in range of x dot shape 0. So this asks me how many rows. Here we know actually know it's a 537 if yi equal to 0. Okay, so similarly, I can do for equal to 1 equal to 2. So this actually tells me how many give me 1 second. This actually tells me the indices for 0, 1, and 2. And of course, here, let me see. I need to know the total number of this so that I can have this. Instead of this one, suppose I have 573, right? I should have kind of like the ceiling function of this. So this gonna equal to np.co. Let me use int because CO is gonna still be the kind of like 3.0 instead of 3. Okay, so let me use int and then I'm gonna have strT of this one. Excuse me. So since I've already have this one, so I can simply have length of 0 list 1 0 plus length of list 1 plus length of list 2. Okay, here we go. So now I have what? Now I have the square root of this one, and I use an int as square root. Let's say 2.9 gonna be 3. So now I have this one. I still have, each pixel, each image gonna occupy 12 pixels, 12 by 12. Although the raw data is on 8 by 8. Why? Because I want to have some space. Otherwise, it will be super, super crowded. So let me see here. Do I need to change anything here? No, I probably don't change. Let me give me 1 second. Let me just plot. Let me just run it. Let me see whether anything's gonna be wrong. Do I have anything? Okay. No, this is the previous one. Sorry. Yes. So I do have all these things. And each here, first of all, you can see there are only 1, 2, 0, 0, 1, 2, 3 digits. And second thing is all the plots are here. So now since I've plotted it, I can train the PCA. But the principle is what? So why do you need to do it? What is your motivation? The motivation is that here I have 3 digits, each digit. Sorry, I should say this. So wait, the axis. Let me still print it. Let me still print. So here x is 64D. Print x.shape. So you can see it's 64D. So now I want to visualize it, and I want to convert the 64D to be only 2D or 3D. And in this 2D or 3D, I want to train, or I want to do the classification, and I want to see the results. So this is the meaning. So what I'm going to do here, I'm going to train and let's say plot 2D PCA. Let me do like this way. So it's gonna show different sections here. I can do the same thing here. Okay, so now I need to train the 2D PCA. So similar thing, model 2D equal to let's say PCA n of components equal to 2. And then no, I think that's it. Then I'm gonna write model 2. Sorry about it. I better have an underscore, although if I'm naming this way, the same no error, but it's kind of like a habit. It does fit x. And then I can, since I fit x, I can just transform it. Model 2D, wait, xpc, let's say 2D equal to model 2D dot transform. Model 2D transform x. So now what I have is I already have the new the data in the new PC space, which is 2D space. Now I can plot it. So since here I already have a picture, so that I will have to create another picture. Fig dot add, I will not plt dot figure, and then ax equal to figure dot add a subplot. And then let's say I will have 2 because 1 is the one 2D, the other is 3D. This one, so I can plot dot plot. Okay, so first of all, what I'm gonna plot is I will plot list of zeros. So here I admit that I'm a bit cheating because technically I already know. But what I want to show you in the plot is if we only project this 64 dimensions to be only 2D, how different the data will be. Because if the data are very different, so I can simply do classification, based on the 2D space. I don't even have to do it in the 64D space, right? Okay, so now I'm gonna say list 0. So I'm gonna show you all the points in of the class 0, and then digit 0, and then PC list 0 as well. 1, and then R dot, and then label equal to digit, let's say 0. Okay, now I can copy and paste for digit 1, digit 2. Okay, so here that's the 1, that's the 2. Two and 1. Okay, so now after it, I can just have X dot legend and then set up the labels X dot set X label. PC2. Okay, now I can plot it. Okay, and you see it looks like this way. And I I'd better add an axis equal so that it won't be X dot six equal. So this is 2D. And you know what? Let me make it a bit smaller to make it, I believe it's gonna be better. And so first of all, the original data is 6040. So we do it in 2D. And you can see actually in 2D, these data already, they change a lot. And let me find out here. So this is original data, 6040, 6040. And here you can see data 0 in our new PCs are actually very different from the data 1 and the data 2. You see it? And indeed, I mean, 1 and the 2 are close, true. You know why? Because we're so, so for example, look at this. For example, look at these numbers. This one is a very bold one versus some 2, if they're very thin. They could be something, close. I guess that's the reason why. However, you know what? We can actually redo it in 3D space. And you will see an even bigger difference here. Space. So basically, I just need to change the thing to be 3D. Okay, now let me see, transform X here, figure. I need to change everything to be 3. Okay, now I will have another thing, which is X dot set Z label PC3. Okay, here we go. But why don't you close that this way? Let me see. Okay, no set Z label. How come? Okay, here we go. What's still wrong? Set Z. Let me see. Did I do something wrong here? How come there's no set Z? Eh? Oh, I know why. Sorry about it. I forgot to make this one. So I need to tell Python projection. It's a 3D. Otherwise, it doesn't understand it. And also, projection equal to 3D. So that's a thing. And then let me see. Set. I forgot to put the title. Let's say, what should I say? Let's say digits 0 to 2, projected in the first 2 PC bases. And then I can copy and paste 3 bases. Okay, here we go. Close all. Okay. Finally, that's the reason why we should not have so many. Sorry about it. Let me close or rerun it. We should have just one. Yeah, here we go. Okay, that's our interesting thing. So this is 2D, and here's a 3D. Let's see. And in the 3D, you can see the difference is even more clear. You see what I mean? So you can see that actually, you know what? Actually, 2D, 3D is pretty similar because I can simply just project like this way. Yeah, because I realize this dimension of the change is very, very small, actually, super small. So, or maybe only for this specific data. No, I didn't use any randomized random numbers here. Yeah, very, very slightly change in the 3Ds. Let me see, did I make any mistakes here? Technically, it should not be. Let me have a look at my, oh, no, not this one. Let me have a look at my slides. Yeah, that's interesting. Let me see. 3D projection to 3D, yes, and then plus 3D. Okay, yeah, there's no mistakes. So, well, but the point here is that we 1012 actually even in the 3D space in the 2D or 3D space, the difference is already pretty good. So that we can directly train this, in the 2D or 3D space instead of in the 60/40 space. And the similar things that for a more complex like a photo or picture or something, you may just set up, first of all, do the dimensional reduction, make the picture includes less information, less data, and then based on the new projected or let's say lower dimensional data, you run to do further things to analyze the data. It could really significantly increase your efficiency. Okay, so this is the second wait, let me see. I haven't. Let me finally plot the things. Let's say I want to plot, here's a 3D. So here it's still under the 3D section, so I don't need to write so many lines here. So let's say explicitly plot the three PCs in the, let's say, original feature space. So in terms of this, I need to have the components, model components, right? So I will create a new figure equal to plt.figure, and then x equal to plot. Let's say I will have, let me think about how many I need. I will have the x bar first. So I will have one. Now I will just simply print x bar. So did I calculate x bar here? No, have not. Okay, so I need to calculate x bar. X bar equals to MP dot mean x is equal x is equal to 0, and then I can just show x bar. Be careful you need to reshape it because here my what is x is just a row vector, so that you need to make it to be 8 by 8 again. And then CMAP equal to binary. So this here I'm showing the x bar, the overall image, the mean average, sorry, and then I can x dot set title. Let's say the mean image. And now I need to write a for to what? I still need to, I can simply copy and paste here. Well, it's j plus 2 should be. And then I will. Okay, so I already have model 3D. So I'm gonna make it to be what? To get the component the PCs. So PCJ means the 0. I mean, again, it starts from 0, not from 1. 0, 1, 2 PCs, and then I need to have the reshape as well. Otherwise, it's gonna be wrong again. 8 by 8, and then CMAP equal to binary again. Okay, so now I should be able to go. Oh, I still have a set title here, so let me also have a set title. let's say the PC. Here, let me use my unit, which starts from 1 instead of PC, 0. So PC1, PC2, PC3. So okay, now let's show it. I should. The truth is it's not tube. For J in 0, 1, 2. Why this one? Let me see. Close all. Oh, not shape, dot reshape. Okay, here we go. So this is the main image, the first PC, the second PC, the third PC. You may need to ask what's the point of this? Okay, the point is here. So they're the same as what I did. So we in the reconstruction for each data X, I will have X equal to X bar plus mu1 V1 plus mu2 V2 and mu3 V3. These mu's are what? Are nothing but the original X projection onto your VJ. In other words, look at here. So using our definitions here, these are mu's are what? Are actually nothing, but let me write it. So I already have, X bar, where is the transform one? I need to find the transform. Okay, XPC3, right? So I already have this one. So in other words, the mu's are actually nothing but this. So let's say if I write XPC, let me do this. So let's say here, let me print XPC3D 0. Okay, so these are the mu's for the first picture. So in other words, my first picture, so many things. Let me just close. Okay, my first picture is wait 1 minute. I'll close 2 minutes. What I mean is this one. So the first picture is here. What I mean is this 0, okay? This very first picture. This equals to 28.48. Sorry, I should start from the bar. So it's equal to this bar picture first plus 2848 times the first PC plus minus 3.434 times the second PC plus 1.032 times the third PC. In other words, now I can kind of like get where are my figures, where are my digits from. So it is from here plus this one times this picture plus this coefficient times this picture plus this coefficient times this picture. And hence the summation gonna go to this picture. So this is how we construct. Again, in other words, you know what? We reconstruct the original image, which was in 64-dimensional space, to a 3D space by what? By the 3 PCs, which are PC1, PC2, PC3. So that is, this is the example here. Wait 1 minute. So this is the thing. The last example gonna actually be a principal component analysis in the eigen phases. So the eigen phases here, scikit-learn itself includes many training data here. So I believe 7 people. Let me see here. Yeah, totally 1288 phases in training data with these dimensions. So each phase is composed of 50 by 37 dimensions. So it's 80, 50. And there are 77 phases of Arrow Shalom, and then all this Tony Blair, he was I don't know how many years ago, the Prime Minister of Britain, and 144 phases is here. So let's see, how can we make it? So basically, first of all, I want to load all these phases, and then I want to print this, and then I want to do the dimensional reduction. In terms, instead of 1850 0 dimensional, I will make it to be only 16 spaces, and then here it's the 16 the reconstructed result. Of course, you can make it to be, let's say, 100-dimensional pieces. The result will be better. Let's see, how can we code it here? So first of all, let me still copy and paste the things from things here. And then what I need to have is just several simple things. First of all, in the front sector learn dot data sets, I believe, or sets. Import fetch. What's the name? Fetch LW people. Yes, here we go. So now I will have people equal to this people, and then I will have, let me see. Give me 1 second. Let me have a look at my code here. Minimum face per person. Okay, and the resize equal to 0.4. Okay. Just very interesting in case I have any mistakes here. Okay, no mistake here. Okay, so now I can load the people. So x equal to people dot data. And then y equal to people dot target. So we can actually print x and y. We can just have a quick look at it. What? What happened here? Looks like still running anything. Wait. Okay, now let's rerun it here. Okay, here we go. So the x data is here. So indeed, x is just as we mentioned here. Or I can just print the shapes. Sorry about it. Okay, here we go. So x is this one, and the y is actually somewhat like labels, and you can see they're indeed like this. So each label is corresponding to a name, so that we need to find the names, and the names would be put here. Names equal to people dot target names, I believe. How come we target? That should be target names. Yeah, let me print names as well. Okay, yeah, here we go. We have 1, 2, 3, 4, 5, 6, 7 people, the names. And then we need what? For each name, I need to let me see here. I believe I printed the total number of names. Yeah, okay. So for each name, I'm gonna print the name so that I can for, let's say, I in range of names dot shape. I can print just there are how many names faces of, let's say, name I. Okay, but how can I write how many? I need to count it, right? So I can use np.sum, and let's say I have already y equal to I. Number 12 names. Okay, so you can see 77 for this, these numbers for this, and now I want to kind of like subplot the training data here. So first of all, I need to have, let's say, a subplot the training data. I can first of all, I need to set up what? I need to set up the sizes. Let me see how can I make height width equal to people dot images dot shapes, I believe. Let me see. What did I do here? Oh, I need an n, not too many, not too little actually. I probably want to use the n here. Let's see whether it's correct here. Yes, that's correct. Okay, so I will have the height and width of this thing so that I can plot the figures. And then I can say for AI in range, let's say 50, I will plot the first 50 images training data first, and then I can have x equal to figure dot add subplot. And then I update one because I start from 0, and then that's the image show xi, but don't forget to reshape it. And that's the reason why I need height and weight. And then I'm gonna have C map equal to, I probably need to add a CM. Let me see, I should be something like CM. Yeah, CM dot gray. So I need to import CM as well. Import, let's say, map. CM. Okay, and it should be CM dot gray. And now I can just have the title. Names I. Okay, here we go. Yeah, let me make the tight. Let me make it too pretty tight. Otherwise, figure dot height layout. Okay, so now no wait width. Sorry. Let me think about it. No, name is yi because y is the name is just the index here. Give me a second here. Name yi. Okay, finally it's still wrong. Let me read it because I forgot to close the previous one. Okay, here we go. So these are the oh wait axis. Let me turn the axis out. Turn the axis off. Sorry, axis. Okay, here we go. It's more clear. No those kind of ticks or axis anymore. So these are our original training data. Then I can do what? I can just do the PC training. I believe here I use a 16. Yes, 16 PCs. So that I will get a 16, train the 16 PCs. And then I can just train the PCA and reconstruct the phases by the first 16 PCs. Sorry, PC phases. Principal, I should say PCs because I definitely, it's gonna be super confusing. So I'm gonna have model equal to PCA, and then let's say M components equal to 16. Model dot fix at fit. I will say fix fit X, and then I can let me see, I can do what, since I have this one. Okay, then I can directly plot equal to PLT dot figure. Let me put this number here. Let's say N. Weeks later, I will change this number. I'll have X equal to figure dot add subplot. Oh, it will still be a problem here because let me think about in range components. Okay. No, let me fix it to be 16. Sorry about it. Let me here fix it. The reason because if I change, I use 100, I still unless I use a square root of this one, but it will make a lot of too small things that we cannot see clearly. So no matter how many number components, let me fix it in range, sorry, range. Let me fix it to range 16 so that I can fix the 4, and then the figures won't be too small. X dot image show. So I'm going to image show model dot components. Why? Because these are the the PCs, the ith PC dot reshape. I'm gonna have height and width here, and now I need to have the CMap equal to cm dot gray again, and then I can just set a title, do whatever we did here, x dot set title. So here I can write, let's say, PC face or PC, let's say I plus 1 I should have, because I want to start from 1 instead of 0. And again, we need to have the axis of. So in this case, we should be able to get figure dot height layout. So in this case, we should have the pieces. Okay, here we go. So let me clear the thing. So this is the 16 pieces. Sorry, it's a bit. Yeah, these are the 16 PCs. And then, in other words, to reconstruct all the things, this is the first most important one, second one, third one, 16. And then we can reconstruct, and then I will make the number to be another number, and then you will see something different. So now I can reconstruct, let's say the phases by the first. Here, let's say use 16 still, because here I use 16 here. I can run different numbers, of course. And then x bar, remember, we still need to get it, equal to np dot mean x axis equal to 0. So what I'm gonna do here is to apply this equation. I need to have, x bar first, and then I will have the PC times the VT here. And actually, VT, the notation in Python, again, it's the transpose. So anyway, I better directly write code, so you will see it. So that I can have, first of all, this one, and then I have XPC equal to model dot transform. So I will have this XPC, I have X bar, so I just need to times the V. But what is V? V is actually nothing but model dot components. X reconstruct equal to XPC. This at in Python, actually in NumPy, I should say, is the matrix multiplication. Model dot component, okay, plus X bar. Okay, so be careful for here, as in our notation, we have a VT because we define V to be in this way. In other words, each vector of the PC is a column, vector. But here, Python, again, remember, they make everything to be row. In other words, your VT here is directly this one. You don't need to make dot T anymore, because if you make dot T, it will be row. So that's the thing. So I have the reconstructed this one. Now I can plug it, right? So I can open another figure, make sure I close everything. Okay, so figure equal to plt dot figure, and then this time I just need to give me a second. I'm gonna plot for all of them range 50. This 50 is the first 50 faces. X equal to figure dot add subplot. So here gonna be 510i, and then X. Actually, I can just copy and paste. Anyway, I'm lazy. And show of X reconstructed. I dot shape reshape. A by not a by 8 anymore. Height, width, and then C map equal to cm dot gray, and then set another title, which is names again. Okay, let me just copy and paste tired. Okay, so now we should have 3 figures. One level, two figures. Wait. Give me a second. Let me see the. We should. Here's the title layout is wrong. So which line? 35 type that's just title layout. Well, again. This one is. Oh, I plus one should be. Okay, no mistakes. Oh, great. Okay, so these are my original training figures. These are my PCs, and these are the reconstructed images. So clearly you can see that the reconstructed figures compared with the original figures, they're not that nice, isn't it? and from let's say Bush. Well, I can still one minute. Let me. I can still recognize Bush, but the face is not that clear. Then what should we do? A very simple way is what? Very simple way is instead of make this. Let me first turn off everything. Instead of make let me see where the thing component to be 16, I'm gonna make it to be 100. So the result will be better. By comparison, 100 is still a very small number because my original data dimension is 1850. So it's still okay. Here we go. This result is actually way better than the 16th result, isn't it? So this is the thing. This is how we can use PC to reconstruct the data. So what's the difference? The difference is that here each image is 1850, the dimension. Here each image is 100 only. You can see most of them, the results are pretty good. Like George W. Bush, I can immediately recognize Bush. This is the what's her name? The guy from Venezuela at the time. Yes, Chavez. So here we go. And then if you want to have an interpretation, then here's so these two slides are added by I just newly added it. So an interpretation here to save my time, I'm not gonna code it here. The meaning is here. So let's consider the first figure. Here we consider still what? Still the 16D. Okay, let me go back to the 16D. Let me close everything. Make it to be 16. Where? Okay, here we go. So the first figure is this figure. So let me make it a bit bigger. So I'm talking about this specific figure. Okay, now I can write it into this way. So here are my 16 pieces, right? Here again, I go back to the 16 components to recover or reconstruct the image, and then the new image is gonna be in this way. Again, I mean 16th. So the results are not that good. So what I have is this is the X bar. So here we go. So this is this X bar. The X bar image is this, and the reconstruction image is this. So now what I have is X PC VT plus this one. So you can see here, if you run the code, I'll show you in the slides. So it will show you the coefficient of everything. The coefficient of nothing is just this number X PC, which is actually, as we mentioned, the definition of score. So the PC first, the score is negative 1.32. PC second is 0.47. In other words, what I have is actually this. So this reconstructed figure, oh, here, there's a typo. This is the original figure. I should use this figure, which is the reconstructed figure by 16, the first 16 PCs, equal to negative 1.32 times this figure plus 0.47 times this figure plus 0.52 times this figure until the last one, the last PC is negative 0.91 times this figure and plus my shift figure. So you sum everything together and then it will give you this face. Okay, so this is the thing. You can absolutely run it to 100 PCs, but the reason again, I mean, I will plot 100 sub PCs. This one subplots it will be too small for my screen to be shown. That's the reason why I construct on 16 PCs. So this is the meaning of PCA. Again, it's just a shift in the rotation and a project the original data to be, a new coordinate system such that my differences will be the most. In other words, I try to capture the most important information. Okay, so that's the thing. And here, there's something for fun here, I believe, which is just the PCs. You can it uses the neural network probably to generate. Let me just random so that you have 30, I believe 32, PCs, and then you can change these things, and they will get different faces. Like for example, this can even change female and the male, and then this one is something like the head, the directions, and this is more like the clothes, this part, and then this is something like here. And indeed, you can see, I mean, the last PC, the change is smaller. The first one is a huge change. You can even change from male to female. Oh no, this kind of like a clothes. The second one is male to female, something like this. I can play with this one, and the video shows that this. Let me close this. The video shows there's a YouTube video here. This video shows that it actually uses a PCA plus a neural network to train the things here. I believe here's a structure or something here.
Samples from one space.
So that thing, and it uses so many training, person, and then construct PCs, and then use this 32 PC to reconstruct the image. And hence, here we go. That's how you can play this for fun. You can just always have a random. Okay, so here's everything of our PCA and also everything of our class. Thank you so much for this very short term of the class. I hope I have more time because usually, a semester, the class usually is composed about like 36 hours. But unfortunately here we only have 6 weeks and also technically 24 hours for the class. It's pretty short. I wish I can include more things, like introduce more libraries. The good thing is that you will have, this is class number 1. Let me see here. Yeah, this is technique 1. You will have technique 2 as well, but technique 2 will be taught by another person, I believe, not by me. Yeah, if I have time, I will gradually try to construct a more like really the online version, more formal version of the AI classes. There are so many AI classes online. In many of them, in my personal view, the better point is that it just shows you how to code. Let's say, okay, here the PCA code is here, and I show you super simple expression of the PCA. But that's just my personal view, that without the mathematics, you want to very clearly know what does a technique really do. That's the reason why I try to include those mathematics here as well, together with the coding things here. I hope this is gonna not be too bad. I know if I only introduce the code, I can introduce a lot of topics, but still I would prefer everybody knows what is the algorithm, what is this method really, doing, because mathematics is the soul of the algorithm, the soul of the whole machine learning things. And also, well, I don't know whether they will have like level number 3. If we have like level number 3, after introducing like technique 1 and 2, you should know the basic things plus the neural networks as well. Then we can introduce a bit more advanced topics like the transform, like ChatGPT. What does ChatGPT really doing here? And also, like in the past year, very famous diffusion model. So what is diffusion? But diffusion model needs a lot of mathematics. really a lot of mathematics there. Otherwise, you want to know what the differential model mean and why we can generate, different pictures based on one picture, and why we can just, based on just one single picture, I can generate several seconds of the videos, how these things all work together. These are actually based on differential models, and you're gonna cut the picture into many subspace and then train it, and then use the neural network to retrain it again, then tune the parameters to make this. Anyway, due to time limit, I will stop here. Again, thank you so much. And please pay attention to the final exam tomorrow, which I'll try to release it tomorrow morning. If not, then I will release it tomorrow afternoon. But once, the things released, I will send you an email showing you the link and also the deadline. And then after you finish it, just email me your final exam. And also don't forget the homework number 2 due tomorrow night. Okay, so that's everything. Thank you so much and have a good night. Bye-bye.